Okay, so in this video we're going to continue with our lessons on exponents, namely real number exponents, and then continuing on to the exponential function. So real number exponents means that we are going to expand our definition of exponents in general to include real numbers. So any real number at that. So up until this point we've been looking at integers, whole numbers, and rational numbers. And now we're going to expand that definition to include irrational numbers. So you can get something to the power of pi, or the power of square root of 2, or square root of 3. Okay? But what's so great about that is that now we can extend our definition of exponents into what's called the exponential function. And so the exponential function, if b is greater than 0, so your base is positive, okay? And not only that, but it can't equal 1 because that would be boring, right? Imagine 1 squared, 1 cubed, 1 to the 4th is still 1. That's why we don't want to include it, okay? So greater than 0, so it's positive, and not equal to 1. The function defined by the equation y equals b to the x is called the exponential function with base b. Okay, and so we're going to look at essentially just a whole bunch of equations with exponents in it. That's it, all right? So if we look at number 2, number 2a says 7 to the cube root times 7 to the square root of 2. Okay, so we've got 7 to the square root of 3 times 7 to the square root of 2. Now, we know from laws of exponents, which include irrational numbers now, that we can just add our powers, right? Because our base is the same. So we're going to do that. So we get 7 to the square root of 3 plus square root of 2. Now we know from our work with radicals in general, in chapter, I think it was 8, or 7, that you can't add two radicals together unless they have the same numbers underneath, right? So that's our answer. We can't do anything with it. Okay, so then let's move on to B. B says 7 to the square root of 3 quantity squared. Now we know that when a exponential function or exponential equation in general is raised to another power, we can multiply our powers. So when we multiply 2 and square root 3, we just get 7 to root 3. And we also know we could break this apart again, right? And rewrite it as 7 squared to the square root of 3. And 7 squared is 49. So this is 49 square root 3. Okay? For C, C says that we have 7 to the square root of 3, all of that to the square root of 2. And now, using what we did in part B, we can just multiply our two powers together. So we have 7 to the square root 3 times square root 2, which we know is 7 to the square root, and then we multiply what's underneath, and that would be 6. Okay? And lastly, in D, it says 7 to the square root of 3 plus 2, so that's all in the power, okay? And for those of you that write large, please make sure you're really showing that that's the power and not a number, because otherwise it might look like a number to me, over 49. So what we're first going to do is we're going to try and get the same base, right? Because we really can't do anything with laws of exponents until we get the same base. So we have 7 to the square root of 3 plus 2 over 7 squared. And we want to try and simplify as much as possible. So what we're going to do is we're going to bring up the denominator and change the exponent to a negative. So we got 7 to the square root of 3 plus 2 times 7 to the negative 2. Now that our bases are the same, we can combine the powers by adding. So we get 7 to the square root of 3 plus 2 minus 2. So we get 7 to the square root of 3. Okay? So then let's move on to something more difficult. Let's start off by looking at number 8. 8 says that we've got 6 to the square root of 2 times 6 to the square root of 8 all over 6 to the 3 times square root 2. So first thing we're going to do is we're going to simplify that second power, square root 8, because that's the same thing as 2 root 2. So this simplifies to 6 to the square root 2 times 6 to the 2 root 2 all over 6 to the 3 root 2. And then because we've got the same base in the numerator, we can add those powers. So we've got 6 to the 3 root 2 over 6 to the 3 root 2. What does that look like? That's right, it's the same number over same number, so it's 1. Okay, let's move on. 14. It says 25 to the 2.4 over 5 to the 5.8. Okay, first thing we gotta do is get the same base. So we know that 25 is the same thing as 5 squared, so we're going to rewrite that as such. and then copy our denominator because we didn't change it. We know that when we have a power to another power, we multiply those two powers, so we get 5 to the 4.8 over 5 to the 5.8. That means I can now bring up my 5 to the 5.8 and combine my powers, right? And so it's going to end up being 5 to the 4.8 minus 5.8, which is the same thing as 5 to the negative 1, so my answer is 1/5. Now let's look at 20. So from here on, that was all pretty much just getting you guys used to working with irrational numbers rather than real rational numbers or integers and such. Now we're looking at solving exponential equations. So if you look at your notes real quickly, I line out the steps for solving an exponential equation. First thing you got to do is express each side of the equation as a power of the same base. Okay, so we know the smaller base here is 5. So we're going to try and get 125 into the same base. Even though the power is going to be different, the base part is the important part. So I know that I can first rewrite what's on the right in terms of rational exponents, right? And then 125 is the same thing as 5 cubed. So I rewrite that. And then 5x is equal to 5 to the 3/2. Now that I've got the same base, the next step is to set the exponents equal and then solve. So I get x is equal to 3/2. That's all the solving I need to do. From there you check your answer. That's step 3. So we plug in 3/2 into our original equation at the top in white. So that's 5 to the 3/2 is equal to square root of 125. It's the same thing as square root of 5 cubed equals 125. Square root of 5 cubed is square root of 125, which is indeed equal to square root of 125. So yes, our answer does work. Let's look at a different one. For number 24, we're given 49 to the x minus 2 is equal to 7 times the square root of 7. So we got to get these into the same base. And I notice that 7 is the smaller base of the two. So I'm going to try and get 49 into a power of 7. And 49 is equal to 7 squared, right? So I'm going to rewrite this as 7 squared to the x minus 2. I notice that what's on my right, 7 root 7, is kind of complicated. So I'm going to rewrite that as 7 times 7 to the 1/2 using rational exponents. Then I want to simplify my powers as much as possible on each side. So I've got 7 to the 2 times x minus 2 is equal to 7 to the 3/2 because I've got 1 here and 1/2 on the other 7. Add those together, you get 3/2. Okay, now that my bases are the same, my next step is to set them equal to each other. So I've got 2 times x minus 2 is equal to 3/2. I'm going to divide both sides by 2. I get 3/4. X is equal to 2 plus 3/4. Common denominator is 4, so 8 plus 3 over 4, which is 11/4. Then we quickly check to see if that actually works out. We get 49 to the 11/4 minus 2 equals 7 root 7. 49 to the, what is that going to be, 3/4 equals 7 root 7. It's the same thing as the 4th root of 49 cubed equals 7 root 7. So this is going to be 7 4th root of 49 equals 7 root 7. 7, sorry, my pen's not writing again, to the 7 times 7 squared to the 1/4 equals 7 root 7. This is 7 root 7 equals 7 root 7. So check, that does work. Okay, let's look at 28. So in 28, it says 6 to the x plus 1 equals 36 to the x minus 1. So again, first thing we're going to do is try to get the bases the same. I noticed 36 is larger than 6, so I'm going to try and get that into a base of 6. So I got here 6 to the x plus 1 equals 6 squared to the x minus 1. This is 6 to the x plus 1 equals 6 to the 2 times quantity x minus 1. And then set my powers equal to each other, since my bases are the same. And then try and solve. So I get x plus 1 equals 2x minus 2 by distributing. I'm going to add 2 to both sides, and I'm going to subtract x from both sides. So this is 3, and this is x. X equals 3 is my answer. When I do a quick check, I get 6 to the 4th is equal to 36 squared. 6 to the 4th is equal to 6 squared squared, so 6 to the 4th is equal to 6 to the 4th. All good. Let's look at the last one of these. In 32, it says 3 to the 2x minus 10 times 3 to the x plus 9 is equal to 0. Now this is kind of complicated looking. So what we're going to do is we're going to set up what's called dummy variables. And we're going to say let y equal 3 to the x. So in order for you to see that this is going to work out to be a nice quadratic, we can rewrite our first term here, 3 to the 2x, as 3 to the x quantity squared minus 10 times 3 to the x plus 9 equals 0. So this should look kind of familiar. We did this at the end of first semester. So now that I've got my variables kind of set up a little more clearly, we're going to sub in our dummy variable, which is y, for every time we see 3x. So this is going to become y squared minus 10y plus 9 equals 0. I'm going to factor this into y minus 9, y minus 1. I get y equals 9 or 1. That's not our answer though, right? Instead, we have to take those two answers and plug them back in. So 9 is equal to 3x, or 1 is equal to 3 to the x. In order to solve exponential equations, first step is to get the same base. So I get 3 squared is equal to 3 to the x, so x is equal to 2. For that second one, 1 is equal to 3x, it's a little tricky looking because obviously the bases are never going to be the same. Now here's the nice thing. There's only one power that makes any base equal to 1, and that is 0. So if you ever see something along those lines where it's b to the x equals 1, that x has to be 0. That's the only way you can get 1 as an answer. So my x's are 2 or 0. Now we're going to take a quick break from solving exponential equations and look at graphing exponential equations. Okay, so exponential equations are curve-like in their graph. Okay, they don't look like lines, and they increase exponentially. So I know it's kind of bad to define something in terms of what you're trying to define, but the way to think of it is that it's going to either increase really fast dramatically, or it's going to decrease really fast dramatically, and it's going to be kind of obvious when you get to it. And you're probably wondering, well, how the hell do I graph this thing? Set up a t-chart. So what I would do is, let's look at this first one here, y equals 2 to the negative x. If we plug in values for x, we'll get values for y. So I'm going to plug in 0, 1, 2, 3. Okay, because that's kind of easy. So 0 is 2 to the negative 0, which is just 2 to the 0, so that's 1. 1 is 2 to the negative 1, which is 1/2, not negative 2. 2 is 2 to the negative 2, which is 1 over 2 squared, which is 1/4. And 3 is 2 to the negative 3, which is 1 over 2 cubed, which is 1/8. So we start off with whole numbers, and we're going to get larger and larger fractions in the denominator. We're going to get smaller and smaller fractions because our denominator is going to get larger and larger and larger. So when we graph it, we'll plot the points we used. So we've got 0 and 1, right? And then we did 1 and 1/2, 2 and 1/4, and then 3 and 1/8. So there's our graph right there, that red line. This is y equals 2 to the negative x. What we're focusing on here is not necessarily the graphs of exponential functions, but rather their transformations. So the transformation we're looking at here, it looks to be a transformation in the y, because we're adding 3 there. So I'm going to rewrite this as y equals 2 to the negative x plus 1 minus 3. And then I'm going to do exactly what I just did before. I'm going to take a t-chart and plug in the exact same values. I want to use the exact same values because I want to see what happens when I plug in the same values into a different equation. Is it the same? Is it different? What kind of things happen here? So we have 0, 1, 2, 3. So this is 2 to the negative 0 plus 1. So this is 2 to the negative 1, which is 1/2. Then we've got 2 to the negative 1 plus 1, which is 2 to the negative 2. So this is 1/4. And then we've got 2 to the negative 2 plus 1 equals 2 to the negative 3, which is 1/8. And I just realized I haven't been adding 3, so I got to subtract 3 from each of these. So this is actually going to be 5/2, 11/4. These are all negative too. And negative 23 over 8. Okay. And so then we plug in our last one, 3, so we get 2 to the negative 3 plus 1 equals 2 to the negative 4, which is 1/16 minus 3. That's going to be negative 47 over 8. All in all, not very pretty numbers. So we're going to try and plot these. We got 0, 1, 2, and 3. So 0, we are down at negative 5/2, right there. Okay. Then 1 is negative 11/4. 2 is negative 23/8. And 3 is negative 47 16ths, not 8ths. There, that's a typo. Okay, and so there's our graph, that second line in red. So that's y equals 2 to the negative x plus 1 minus 3. So 2 things to note here. Not only did we shift down essentially 3 here, right? We shifted down 3. We also shifted to the right quite a bit there, to the left, sorry, quite a bit. So the numbers that we got before in these ones was like this is 1/2, right? And this is 1/4, and this is 1/8, and this is 1. Now we've got values. This is now 5/2, negative 5/2. This is now negative 11 over 4, and this is now negative 23 over 8. So we kind of shifted this direction and down while it was at it. So this one was going to go there. Okay, so it's a little wonky looking, but that's what they want you to do. They want you to graph them on the exact same axes, and that's all I'm saying. Just take 3 or 4 points in this case. I would always conclude 0, but any other numbers are up for grabs. 0, 1, 2, 3 are pretty easy to pick, so I mean that's usually what I would do. And then just graph them and see kind of what kind of transformation do you get. Is it vertical, horizontal? What kind of shift happens to the graph? Okay. All right, last problem, 38. 2 to the 2x minus 1 minus 3 times 2 to the x minus 1 plus 1 equals 0. So if you're already guessing we're going to use dummy variables, you are very smart and catching on quickly, and which all of you are. Okay, so first thing we're going to do is I want to try and isolate the x exponents. So I want to get the variable x in the exponent by itself. So I'm going to use laws of exponents to break up my first term into 2 to the 2x times 2 to the negative 1. Right? Because the exponents are being added together, so I can break them apart by multiplying the bases. Minus 3 times, and then I'm going to do the exact same thing. So I'm going to 2 to the x times 2 to the negative 1 plus 1 equals 0. From here, I'm going to drop that 2 to the negative 1 into the denominator so that I can make it a positive exponent. And then I'm going to multiply both sides by 2 to get rid of those fractions. So I get 2 to the 2x minus 3 times 2 to the x plus 2 equals 0. From here, I'm going to let my dummy variable, y, take the place of 2 to the x. So I get y squared minus 3y plus 2 equals 0. So y minus 2 times y minus 1 equals 0. Y equals 2 or 1. Take that and plug that back into my dummy variable. So 2 to the x is equal to 2, or 2 to the x is equal to 1. So I get x is equal to 1 or 0. And that's my answer. Okay, and the classwork is due the 2nd of March, that's Thursday for C block, and the 3rd of March, that's Friday for F block, and it's page 461, numbers 1 through 37 odd. Hopefully most of this makes sense. I will be available Thursday and Friday for any questions you may have. All right?